Ladies and gentlemen, dear colleagues, welcome. My name is Daniel Hanzalek, and you are watching the 70th talk of the scheduling seminar. Today, I'm happy to introduce Kwon. He is Associate Professor in Industrial and Systems Engineering at KAIST in Korea. His research interests are in computational optimization methods for efficient transportation and logistics systems. Today he is associate professor, but he received his PhD in industrial engineering in 2008 from Penn State University. And a part of his work, he likes programming, especially in Julia. So, Shenyang, it's very nice to have you here, and please go ahead.
Thanks for the nice introduction. So here today I'll be talking about some learning-based approaches for solving transportation optimization problems. And today, instead of delving into really a single topic and a single research, but I want to introduce a stream of research that I've been doing recently. So as just another introduction, so I'm a professor also, but I'm also a CTO at a startup company that has been existing like for 2 years and a half by now. It's called Omelet. It's called Optimization and Machine Learning Technologies. So the company's names reflect what I've been doing in the research as well. But anyway, today's research talk. So today we'll highlight my activities as a professor. So I'll be talking about mainly about the vehicle routing problems. So various vehicle routing problems are there, but I think many of you are familiar with this one, the capacitated VRP, CVRP. It's a very standard topic in the VRP world. So a given set of customers, and there is a vehicle capacity, and we want to deliver the parcels or packages to customers within the shortest distances traveled. And in here is to minimize the sum of the total distance traveled by the total vehicles is the objective. And we have to determine the sequence of the assignment of which customer to be served by which vehicle, and then their orders. And this is a practical VRP problem we have been solving in the Omelet company. And this is the result of the VRP algorithm. And in this problem, we had to deliver to many customers within a certain time frame, and each vehicle, and you see the different colors, and each route means one vehicle, and this vehicle has a capacity of like about 15 customers. So at most, one driver can visit at most 15 customers. So we have to split the customer set nicely so that we can finish the delivery within the certain time. So this is a zoom in the Gangnam district in Seoul. It's a very populated area of Seoul. And you see that, I don't have a really good visual of the actual location of the customers, but it shows the route that the vehicles taken. And this is another part in metropolitan area. And this is also same vehicle capacity, 15. So we'll be talking about something like that throughout this talk. And vehicle routing problem is an NP-hard combinatorial optimization in general, and there are many, many different approaches. So first class is exact method. So these are like providing provable optimal solutions, mostly model-based and theory-based. And so branch and cut algorithm, branch and price algorithm, and their combinations, branch and cut and price algorithm are the main things. And meta-heuristics are also there, genetic algorithms and large neighborhood search algorithm, and of course there are local search methods. And recently, deep learning methods are arising in our interest, and sometimes they are called neural combinatorial optimization. So here's a very a brief overview of what generative models are doing for translation. So if we are given, say, a sequence of words in English, then generative model can translate into another sequence of another language. So if you think about that as like a high-level input and output model, and then we can think of like, what about if we input a sequence of number, and then the generative model or some other neural network model can translate into another sequence. So this is exactly the situation in the traveling salesman's problem, actually. So we are given some n number of cities, n number of locations of customers, and then we are interested in finding the shortest tour, visiting all cities exactly once, and then coming back to where we started. So if you think about in the framework of the neural network model, now instead of input sequence, we actually are given a set of customer nodes. So it's a node numbering. So node numbering can be arbitrary. So we are talking about a set instead of sequence. And then we should be able to translate into a sequence of numbers over here. So how it works is, so we start from a starting point, and then the input is increasing here as y increases as we make a progress, and then this neural network model predicts which node will be the next node. So it recursively calls this neural network model with different style of the input, and then it outputs the next node. So here's the quite successful model so far. In 2019, there was a paper by Kwon et al., and they used the transformer-like encoder-decoder model. And then next, in each step, it predicts which node will be visited the next time. So it provides the probabilities of each node to be chosen as each step. So these kind of models are called end-to-end learning model. So it learns a heuristic algorithm basically, and it provides an approximate solution. So if we're given an input, and then there's a neural network model that outputs a solution somehow, and there's no other logics behind it, then it's called end-to-end. So here's an example application of this end-to-end approach. So instead of just solving a traveling salesman's problem, but we can also solve traveling salesman's problem with drone. So this problem, TSBD, is a collaborative delivery problem between the truck and a drone. So, many years ago, several years ago, many logistics companies have been testing like a drone launching from a truck and then make a delivery, and then they come back to truck and so on. So for this problem, we can create some hybrid model that combines the transformer-like encoder, is an attention-based model encoder, and then decoder, we use the LSTM. So creating this hybrid combination, we were able to learn the heuristic to solve TSPD. But the entire framework remains the same as before. We have a neural network model that accepts the customer locations as a set, and then it outputs as the sequence of the visiting. So these are the results. If you see on the left-hand side, left column, they are a true optimal solution solved by the mathematical optimization, and in the right column is the neural network model's output. So if you take a look, they are almost same, but sometimes there's a gap of like a very small gap here, 1% or 0.69%, and their shapes are pretty much same, but there are minor differences over here. And same here, but sometimes you can see that gap can be up to 5%. So these models, like the end-to-end models, are really nice, but there are pros and cons, like every model. So pros are like fast computation is possible, and then they are parallelizable on GPU because it's a machine learning model and the neural network running on GPU, so you can solve many different instances at the same time. But there are cons as well. They provide quality solutions, but sometimes it can be very bad time to time, and it's not quite predictable, and it's also not as good as mathematical optimization solutions, and it requires a long training time. So now people are interested in creating hybrid method. So there are good things about the learning-based method. And there are also, disadvantages as well. So to overcome those disadvantages, we can combine with the existing or new optimization heuristic algorithms and meta-heuristic algorithms and then exact algorithms as well. So today we will go over these three classes approaches. So first are heuristics and meta-heuristics combined with learning. So this is one example. Say in here, so machine learning models are used to guide heuristic algorithms for solving some optimization problem for faster computation. So if you see here on the left-hand side, the green lines are representing the horizontal axis represents the time, the computational time, and vertical axis represents the gap. So green line represents some heuristic algorithm, and it reduces the gap as you go on with the time. And now, when you combine with the learning model, we were able to reduce this computational time significantly. So, for example, say arriving at the end, it converges in 3 seconds, but with the neural network model, and then you can make it converge like 1.5 per second. So, I will tell you about a little more detail about this. So again, this is about solving TSP with drone problem. So in TSP drone, there is a dynamic programming approach for, called exact partitioning. So if you are given some TSP tool as an input, then using dynamic programming, you can divide partition customer nodes into nodes served by drone, here orange nodes, and nodes served by the truck, which are green. So this partitioning is based on this sequence of the optimal TSP tour, and then this dynamic program provides the optimal partitioning. But of course, this is a nice thing, but it takes quite time because it's an exact procedure, it's a dynamic program for really large scale problem, it takes forever. So to overcome the difficulty, we came up with some iterative method. So in this iterative method, it looks at some subsequence of this TSP tour, and then it tries to improve it using dynamic programming. So in this case, because we are focusing on some small subsection of the entire problem, dynamic programming takes a very fast computation time, and then you can just iteratively improve your solution. But now we are interested in making it even faster. So instead of running dynamic programming actually, we are interested in using neural network as a surrogate model to learn to predict the outcome of dynamic programming. So using the graph transformer structure here, graph transformer structure with the graph normalization layers and so on, we are able to learn. The input is some subsection, sequence of the TSPD solution, and the output is cost prediction. So now for using this, instead of running dynamic programming sub procedure, actually, we are just learning the neural network model to have a cost prediction. And the result again is the reduced computation time. And then if you see here, iteration time. So in each iteration, neural network model closely follow the original heuristic algorithm in terms of the iteration versus gap. But each iteration takes a shorter time, so we can see the time saving here. So we can say that machine learning model guides heuristic algorithm, and then it enables fast computation. So this is one example of how we combine learning model with heuristics. The second class is metaheuristics. So metaheuristics is like a genetic algorithm, and designing a good genetic algorithm or other evolutionary algorithm is quite challenging sometimes for a problem, certain problems. And also, if you don't spend a good time for designing good metaheuristics, it'll just take long computational time, and then it delivers a poor result. And here, now we are again using the neural surrogate, and here's the application problem. So instead of just a single depot BRP problem, we are considering multi-depot BRP problem. How we solve this problem? Now we are given the 3 locations of depots and then a set of customers here. So now we have to determine which customers will be served by which depot. So maybe you can come up with some customer depot assignment plan. So this is just arbitrarily drawn by myself. And then maybe within this assignment, and maybe we can run some routing algorithm and obtain the solution. Is this a good assignment? Maybe you can try another thing. So another trial, we can come up with some another kind of assignment, and then we can solve routing problem again, and then we can decide if it is good enough or not, and then if it is not good enough, we can try another things. So that's the main idea of this genetic algorithm. So in the chromosome level, we are only talking about the assignment. And then routing problem is used to evaluate this chromosome. And with the chromosome representing the assignment, customer depot assignment, and then routing problem is solved for each chromosome, and then we can come up with evaluation. Now, of course, this routing problem itself is a strongly NP-hard problem, so it will take very long time for a larger scale problem. So we don't want that. So instead of actually solving the problem, we come up with the neural surrogate model. Again, that receives the VRP instances as an input, and it outputs cost prediction. And then it gives the cost evaluations for multiple chromosome at the same time with the parallelized GPU computation. So it has advantage in the computational time as well. So the result is following. So GenCP is the our genetic algorithm with neural cost predictor, and the Vroom is a quite popular open source software that can solve MDBRP, multi-default vehicle routing problem. So if you see here, the cost is ours is a little slightly better, but not quite much. But if you look at the time component, so for the larger scale problems here, more than about 1,500 customers, we see the reduction of the computational time. Is it a good thing or a bad thing or good enough? Is there any advantage, disadvantage discussions? Yes, there are. And of course, this GenCP is a heuristic framework that can be utilized to many different kinds of problem, but also we have some weakness as well because this is based on the learning model, and the machine learning model sometimes is the output is quite unpredictable, is not very robust, so we can see that it needs to be improved. But the main lesson is by doing this, utilizing the GenCP framework, like combining the genetic algorithm with the machine learning-based cost predictor, is a neural surrogate, we can approach many different kinds of problems using the same framework. So even if we don't have a right solver for the very new class of problems, we can still use this framework. I mean, at least there's a very convenient heuristic algorithm. So these kind of approaches are gaining interest. And now we question, where are we actually heading for? So we talked about these things again. So optimization algorithms are good. I mean, we have been tackling this kind of optimization problem, like a TSP problem, capacitated vehicle routing problem. I mean, these kind of problems have been long studied. So we understand about this problem very well. So human developed algorithms, either exact algorithm or heuristic algorithms, are really performing excellent. So now deep learning based model still lagging behind, like in terms of the performance. If you see here, like a SIM NCO kind of model is a TSP 0.47% of gap. I mean, it's impressive, but still there's some gap. And if you move on to a more difficult problem, like a pickup and delivery problem, here you see like a 10% gap here, and then a price collecting TSP problem, there's like a 2 to 11 for about 15% of the gap. So whatever we do, there will be some gap, like the optimality gap will be still there. And then how can we improve that? How can we overcome that approach? Now, in the end, the goal of this kind of end-to-end or meta-heuristic algorithms goal is to come up with some foundational model that can solve any kind of combinatorial optimization problem. Let it be like a TSP, weak routing, or scheduling, right? But we know that, as we have seen, this whatever we develop here, neural network model, is not guaranteed to produce the optimal solutions or very good solutions. So likely story is we need something to improve it. So automated improving search algorithm is necessary to complete this chain of automated algorithm development. So early on this year, Jensen Huang from NVIDIA also emphasized the importance of like a test time scaling, test time search, test time computing, or reasoning. So this step is to utilize the pre-trained neural network model at the inference time or test time to maximize its output. So again, let's come back to this model. So when you talked about the attention model for this transformer-like encoder-decoder model, we have seen there are some bars here. These bars representing the probabilities of each node will be chosen as the next node. So probabilities. And then depending on how we interpret those probabilities, we can come up with a different outcome. So one decoding strategy we say is greedy decoding. So when we have many different probabilities and then there are like search trees, and then we can just move on to the highest probability. So as comparing 0.4, 0.6, we choose 0.6, and then next step 0.5, and so on. And then there is something called beam search. Instead of just coming out with one output, we can try to come up with like several outputs at the same time by when you search the trees. But we don't want to go over too many solutions at the same time because it will be computationally expensive. So we want to limit the size of the solutions we are searching. Or we can do sampling as well. So whenever we make a decision, instead of like choosing the highest probabilities, we just randomly drawing among these probabilities and the choices. So there are many different techniques called like a top K sampling, top P samplings, and then depending on how you how you do sampling, you can come up with a different set of solutions. So sampling means that you will be having, a number of solutions later at the final time. And here, maybe we want to a little better than do just sampling. Because when you do sampling, you don't really search for the performance. You're only considering these probability distributions. And then these probability distributions are likely representing good performance, but there is no strong correlation. So instead of just relying on these probabilities, maybe we can search for the better performance at the same time. So in this approach, neurogenetic search algorithm that we have developed, we use the power of genetic search. And we want to emphasize that this approach is universally applicable for various discrete optimization problems. So how does genetic algorithm really work? So, many of us are already familiar with this genetic algorithm, but here's a recap. So when we have some population, and then there's always some new generations are created, and then these are evaluated. Each individuals are evaluated, and based on this evaluation and or fitness score, we select like two parents, and then they are mated, and then they will be their chromosomes will be crossovered, and then with some mutations, new generation, new offsprings are created, and these cycles are repeated. And here, when we develop genetic algorithm, the main challenge is actually comes with this part. So when we do a crossover operations are very expensive. They're very difficult to design. So here's one example. So the design of the crossover operator is very problem specific, and coming up with the very efficient and effective crossover operator is very, very hard. So here's one example. This is like a state-of-the-art TSP algorithm for using the genetic algorithm. So here you come up with one parent and another parent, and then they are mated, and then moving over like many different stages of graph analysis, they come up with the valid tours as their offspring. And inside of this crossover design, the philosophy of taboo searches are embedded. So local search algorithms are already inside of it. So not so easy. But this algorithm is really efficient and effective. So now we want to utilize the already trained neural network. Assuming we have already trained neural network, maybe like an end-to-end model. Now, can you utilize this model for automated design of the crossover and mutations? The key idea is we reinterpret the crossover. So now we want to just generate samples conditioned on the parents. So here's what I mean here. So among the population, we come up with two parents. We can think of it TSP. So one tour, another tour, and then we combine them as we take the union, and then we create this graph. Now, when we run this neural network, this is a P zeta star representing the trained neural network. And when we sample from this, and we just condition on this graph, by the masking operations, we can just restrict our solution generation from this neural network just on this edges on this the parent graph, we say. So we use that, and of course there are many details about it, like mutations are also used, and then there are like some techniques to guaranteeing the diversity of the populations and so on, and the result is quite impressive. Now we use the graph neural network solving for TSP, and then we compared with different kinds of sampling method, sampling and then beam search, Monte Carlo tree search, and then ant colony optimization. And if you compare with this approach, then ours had a better, optimality gap. And also when we do, long sampling, we generate more samples, like the computational time increase like 10 times, and then we can reduce the gap also 10 times. But still lagging behind with the existing optimization solvers, but we are approaching to them. Now, CBRP, the same thing. So we see that we can achieve the less than 1% of gap for a difficult CBRP problem with the large scale optimization problems like 200 nodes and 500 nodes. Our gap is less than 2% over here. And if you compare with the other decoding search algorithms methods, like a sampling and anti-colony, we see that ours is representing the greens, is more sample efficient. If you compare with the number of samples and the gap reduction, we see that ours are more quickly reducing the gap with this the same number of samples. Now, we applied our algorithm for solving TSP, CBRP, and project collecting TSP and the orienting problem. These are all well-known optimization problems. And still, existing optimization algorithm doing much better than our learning-based algorithms. But the main point I want to make is that so the learning-based method, neural network, and then the like a test time search algorithms combined, they can be applied to many different kind of algorithms, even though the optimization algorithms are not existing yet. Another point I want to emphasize is that this neural genetic search algorithm is a test time search algorithm can be applied to many other domains as well, as long as these two requirements are satisfied. So first, we need already trained neural network model to solve the problem. And second is the solution space are tokenizable, meaning that they are discrete. So in routing problem, a token means an edge, and in language problem, a token means a word. So we applied this similar idea to language problems and then worker design problems as well. So in the worker design problem, I have a very little idea about what's going on here, but also is a Merkle structure can be written as a sequence of strings, and that means it's tokenizable, just like the route or the sentences here. So we can combine these to create a better like a Merkle designs and so on. So these are all successful. So good. So now, so far, I've been talking about like a automated algorithm design space, like an ant-fed model. So emphasizes like a neural network model structure. If you train this model well enough, good enough for a certain problem, then you will be able to generate the solutions. And then using test time algorithms, you can even improve those. So then the entire procedure can be automated. So we are, working on there in that direction. Now, as a second matter of second stream of the research, for combination of optimization and learning, I want to talk about exact algorithms. So now, when you combine the heuristics and metaheuristics, these were for automated algorithm design. The third stream is exact algorithm. So exact algorithms are like a branch and cut. So branch and cut algorithm is it is approach that many, I think almost all modern mixed integer programming optimization solvers are taking. And then the main decisions are how to branch and how to cut, right? So branch and bound tree exploration strategies are also studied in terms of the machine learning approaches. And then cutting plane problems are also studied in terms of the machine learning. And here is cutting plane algorithms. So there are two decisions to make. So first is how to generate the cutting planes. And the second strategy is how to choose cutting planes for each iterations. And now I want to talk about how to generate cutting planes. Again, this problem is for capacitated vehicle routing problems. Again, now we want to solve this problem. So the current state, the provably optimal solutions for CBRP is quite challenging. Now, early 2000s, we are focusing on the entire research communities are focusing on solving some small problems, like less than 100 nodes. And branch and cut algorithm was the main thing. And then later on, 2010s and 2020s, now branch and cut and price algorithms are the mainstream. And then this is still the state of the art. But now we are mainly focusing on like 300 and 400 sides of the problem to find the truly optimal solutions. And now, many large scale problems up to 1,000 nodes are still open problems. We don't know. I mean, we can of course find some good heuristic solutions for these problems, but their optimality is still unknown. Compared to TSP world, now back in the 1960s, only 80 cities were served to the optimality. But I mean, with lots of advances in the optimization, like a cutting plane algorithm and branch and bound algorithms and LP solutions and so on, our computational ability increased quite significantly. Now, 20 years ago, 85,000 cities were problems were solved to the optimality, and I used the well-known TSP solver, Concord. I used it to solve 1,000 city problem in my laptop, and then it generated optimal solution in 30 seconds. So which is, I mean, phenomenal. And now people are solving, I mean, even much larger optimization, I mean, the scale of the TSP problem to the optimality. The main thing here was branch and bound and branch and cut, so cutting plane algorithms. So cutting plane algorithm have been playing really a good, I mean, the most significant role in driving this stream compared to CBRP now. So the progress of the TSP optimal solutions were here, and now CBRP still, I think we can say that this is early in the research. Now hoping that we can solve a much larger problem to the optimality sometime soon in the future. So cutting plane, I want to emphasize the importance of the cutting plane. So in the process of the probably optimal solutions, we know that the finding a good upper bound is important, but as finding good lower bound is very important to prove its optimality. I mean, at the end, so our approach is through the branch and bound is to match the upper bound with the lower bound. So the lower bound usually improves slowly, and then improving the lower bound requires generating good cutting planes. So cutting plane. So when you have some LP relaxation of your combinatorial optimization problem, you solve LP, and then you obtain some LP solution. And then if LP solution does not satisfy all the constraint, then you have to satisfy, or it does not satisfy the integrality, then you generate this cutting plane by solving the separation problem. So suppose this one was your LP solution, then it is not truly a feasible solution to your integer optimization problem. Then you generate cutting plane and you cut out this solution. So you separate this fractional solution from your actual feasible space. So here's the integer programming formulation of the CBRP. And we focus on this equation constraint number 3. So constraint number 3 basically defined for every subset of the customer nodes. So the number of constraint in the form of constraint number 3 is exponential, we can say. So, I mean, what this say is basically for every subset of customers, we need to provide enough vehicles to serve the order demand. Like demand here, DI is the customer demand at customer node I, and Q is the vehicle capacity. So then we have to provide enough number of vehicles to serve this subset of customers. So this is called capacity inequality. And then when you use this form of the right-hand side, this provides the some rounded number. So it's called rounded capacity inequalities, which is popularly used in the context of this cutting plane algorithm. So basically, so this is a feasible solution. In this case, nothing to worry about. But when you have when you solve LP problem, you obtain sometimes this kind of fractional solution. The solid line representing the edges with x value equals to 1, so good. But this dotted line representing edges with fractional numbers like a 0.5. So this is clearly infeasible solution to the integer programming. So we want to cut this out. So the idea is to select the proper subset. So if you choose proper subset, and then this can form a violated inequality that this provides a cutting plane to be used. So to select this proper subset, to create this like a cutting plane, there exists some heuristic algorithms and exact algorithms as well, but it takes quite a long time, and then the performance of the heuristic algorithm is not tested for really large scale, so we come up with some neural network-based approach. In our approach, the key idea is the coarsening process. So when you have like an input graph, now we predict the probability that this each node belongs to the same set here. So the main idea is to come up with a proper subset. So we have to create in the end this subset, right? So now if the probabilities are high with these two, between these two, then we merge them. And then so that later on in the end, we only have three like a supernodes. One node representing the depot, one node representing this a proper subset, the other node representing its complement. So neural network predicts the probabilities, and then neural networks are called multiple times in a recursive way. So we use the supervised learning for the instance size, training instance size 50 to 100 nodes, because these were the problem size that we were create some quality labels using exact algorithm, exact separation algorithm. And we compare with the performance with the CBRP SAP, which is a de facto standard heuristic algorithm for solving this kind of separation problem. For small scale problem, we see that CBRP SAP still provides a better solution. So the optimality, because this is optimality gap, so the lower, the better. So here, the small scale, CBRP SAP was better. But if you move on to larger scale problem, then our neural network-based approach was outperforming this CBRP SAP. Now, this winning ratio, if you see that clearly, as you move on above 500 number of customers, then neural network-based approach provided a better cutting plane qualities. So this is quite an interesting one. And now, if you see here, in the top row, representing small problem sizes, like size 100, and then if you move on, 200, 300, and up to 1,000. Now you see the blue line again is CBRP SAP, existing heuristic open source packages, and the orange line representing our neural network-based approach. So as we move on iterations, the gap reduction was more significant in the neural network-based approach than the heuristic algorithms. And even we can improve it using test time search algorithm. Now remember, NeuralSAP, which is a coarsening process, actually come over to say like in the initial one, so we have like a 9 nodes, like 10 nodes actually. The first node 0, it represents the depot. And at the end, in each step, we are merging certain customer nodes into some super nodes, and we keep merging them until we have only 3 super nodes. So depot, and then subset, and its complement. Now we have this history. So whenever we have some successfully identified this super nodes, we trace back. So for example, if we trace back t equals to 5, the fifth iteration, we have this supernode and this supernode. So each supernode representing the group of 1, 2, 3, 4, and group of 5, 6, 7. So by examining this history, then we can find sometimes better the inequalities, better cutting planes. With that, we are able to even improve it. So again, this blue dotted line represents CBRP SEP. Now this brown line is our newest test time search algorithm result. So it can improve it. So we can keep improving it. So again, now I want to wrap up this all the topics that I have been covered. So first we talked about the heuristics combined with the machine learning model. And then second, we talked about the meta heuristic with combined with learning model. And then we also talked about test time search algorithm for covering this number one and number two. And also we talked about how we can utilize machine learning model to improve the performance in the some subroutines that are used in the exact algorithms. And also we can take a look at the test time search approach for, even improving the performance. So these research are sponsored by National Research Foundation of Korea in the name of Beiji Research Lab. And then our group of people like Professor Jingyu Park, Changhyun Kwon, this is myself, and then we too are leading also the startup company called Omelet. And we have other collaborators, Professor Huang, Professor Lim, to come up with to create general framework for solving various combinatorial optimization problem using machine learning and some optimization algorithms in combination. So thank you very much, and I will stop here today for my talk. Thank you.
Okay, thank you, Chang, very much. It was very well structured, I think. And now let me ask if anybody is interested to ask the question. Just please unmute. You should be able to do so. Allow participants to unmute. Okay, so you should be able to unmute. So if nobody starts, maybe I can start. Chang, you spoke mostly about optimization problems where feasibility was always guaranteed, so to say. But we tried also some of these approaches on problems where there is no guarantee that there exists feasible solution. For example, traveling salesman problem with time windows, right? So where time windows might be so tight that there is no feasible solution, or it's like harder to find. The search space is not so, let's say, smooth. There are many traps and so on, right? So, so do you have any intuition or anything to comment on that?
Yeah, thanks for the great question. That exactly the point is where the purely end-to-end approach is lagging behind, I think. So finding like a feasible solution for a very tight constraint problem is very hard, of course, for a neural network to figure out. So that's why we want to, I think it's a hybrid model has a better chance. So I think for that kind of problem, we still want to use like optimization, classical optimization based approach, like constraint programming or like some other search algorithm to search for feasible solutions. But I think we can train neural network model to guide search. So maybe yes. So then we can wrapping the machine learning model with the existing constraint programming kind of approach and externally. Then that way we can guarantee to find the still finding feasible solutions, but at the same time we can try to improve the computational time. I think I think recently there were some studies about combining a constraint program with this kind of machine learning approaches, but I'm not sure which research was it actually here. Yes.
We also published one paper just recently with Optal Solver when we are guiding the search, but never mind. So, so any other question? No question. I would even ask one more. So what do you think? You spoke mostly about, let's say, logistic problems, so vehicle routing and so. So if we look on purely TSP, when we are given set of indices of vertices, and we need to generate, let's say, the best permutation possible, where
Mm-hmm.
we have potentially n factorial solutions, but it's a mathematically very well structured problem. So when we would look into scheduling domain, so the problems of this type could be, for example, permutation flow shop, where you have also n factorial possible solutions when n is number of jobs, and you just need to choose the best possible order of jobs so that you minimize Cmax. So how far do you think that your approaches are transferable to scheduling? I don't know how far you are familiar with all these problems. So do you think that your approaches are exclusively applicable in transportation, or do you have some idea about how far is it transferable to scheduling domain?
Yes. For scheduling, I am not very familiar with with the scheduling domain, but I have been trying, this and that for solving scheduling problem as well. But it was much more difficult. I think that comes with the like a training distributions is problem. So in the logistics problem, it happens usually like in like a two-dimensional space, geographical space. So we have like a coordinates
That is like
and yeah,
planar structure
planner,
of the
yes,
graph
problem
behind.
structure.
Yeah, yeah.
Yes. So I think it seems like that kind of information is easier to learn in the neural network. But if you think about like a scheduling problem, you have like a processing time and then like the precedence constraints, conditions, and so on. Those things are like not easy to represent. So my experience, my limited experience with the scheduling problem was harder based on the learning approach. But if you come up with some nice way of like encoding those information in a compact way, or more like a coordinates, which can be understood as more globally, then we can come up with a better thing. So right encoding method is the key for scheduling problem. So like a graph neural network has been used for like uh, encoding those kind of information. But the main disadvantage of the graph neural network approach so far is that it's not easy to generalize, or it's not easy to like sharpen the performance. So now still there are many things to do with that regard.
Okay, thank you very much. We are very happy as a scheduling community to hear that our problems are more difficult. Okay, so please, thank
Yes.
you. Very tactical answer anyway. So one last call. So anybody has a question? I hope that you are able to unmute. Nobody writes anything in chat. Uh, so thank you very much, Chang. I think it was very informative talk and
Thank you
very
so
hot
much.
topic. So thank you. And now just let me invite you to the next talk, which will be in 2 weeks. It will be given by Zia Zhu from HKUST, and he will talk about efficient and robust large language model interference scheduling optimization. Okay, so it will be even more abstract and even more modern using large language models in our domain. Okay, so thank you very much, and be with us, and I hope to meet you in 2 weeks. The talks are recorded on YouTube, so it takes like 1 or 2 days to put them in polished form, but they are there, and you may observe how many people are watching your talk and so on. Okay. Thank you very much, and good luck. Bye bye.
Thank you very much.
Thank you.
Thank
you.
you.
Bye-bye.
Thank you.